Movement Primitive Diffusion, learning gentle robotic manipulation of deformable objects. Learning motion policies for minimally invasive surgery has special challenges, including manipulating delicate tissue without damaging it, only having access to camera images from an endoscope, and the high cost and limited availability of data from highly trained experts. To address these challenges, we propose a diffusion-based imitation learning method that predicts sequences of actions. We train a model to approximate the score function of the human demonstration distribution with denoising score matching. During inference, we use the learned score function to iteratively denoise a random initial action sequence. Our method uses probabilistic dynamic movement primitives, ProDMPs for short, to generate smooth action sequences with guaranteed initial positions and velocities. Our method, named Movement Primitive Diffusion, or MPD for short, takes observations from previous time steps and initial conditions for position and velocity and returns an action sequence. In MPD, the outer loop alternates between predicting and executing action sequences. The inner loop iteratively denoises an initial action sequence in task space by encoding it into ProDMP weights with a learnable denoising model E, and decoding it back into task space with a ProDMP. An ODE solver uses the predictions to solve the diffusion process probability flow ODE. We evaluate our method against three state-of-the-art diffusion-based imitation learning baselines: the temporal CNN and transformer variants of diffusion policy and BESO. In simulation, we evaluate the methods on 4 surgical tasks, named grasp, lift and touch, rope threading, bimanual tissue manipulation, and ligating loop. We further evaluate our method and the strongest baseline, diffusion policy with a temporal CNN, on real-world setups of all 4 tasks. Our method is able to predict action sequences at 90 Hz, which leads to no noticeable delays between motion prediction and execution. Because we use ProDMPs, both action sequences and transitions between them are guaranteed to be smooth and to respect initial conditions for position and velocity. In contrast, the strongest baseline, diffusion policy, is not guaranteed to respect the initial conditions, leading to jumps between consecutive action sequences. Additionally, the delays between motion prediction and execution are noticeable, as it requires double the inference time compared to our method. In our experiments, we show that our method can manipulate deformable objects gently, guarantee initial positions and velocities, and model multimodal behavior. Compared to the baselines, our method is more data efficient during training and faster during inference. ProDMPs further allow our method to predict raw actions at a higher frequency than the training data for high-quality robot control. Characteristic for imitation learning methods, MPD shows limited robustness for out-of-distribution data. However, the diffusion framework mitigates this limitation to some extent compared to other imitation learning frameworks.